Welcome to MatSci Simple, where engineering and science is broken down into simple, clear, visual explanations. Subscribe so you never miss a new episode. Alloy design. Welcome back. Today we are covering alloy design, why there are thousands of different metal alloys, and how engineers choose the right one for the right job. We will look at 4 ways to make metals stronger, then move through steel grades, aluminium, titanium, nickel and copper alloys, and finish with real engineering case studies. Strengthening mechanisms. Pure metals are too soft for most engineering applications. Engineers use 4 mechanisms to strengthen them. First, solid solution strengthening. Solute atoms are added into the host lattice. They distort the crystal structure. This distortion creates obstacles that block dislocations from moving. The more solute atoms, the more obstacles, the stronger the metal. Carbon and iron is the most well-known example. Second, precipitation hardening. Through a heat treatment sequence, solution treating, quenching, and aging, tiny second-phase particles form inside the matrix. These particles are far more effective at blocking dislocations than individual solute atoms. Third, grain boundary strengthening. We covered this in the previous episode. Smaller grains mean more boundaries, more barriers to dislocation movement. The Hall-Petch relationship. Fourth, work hardening. Deforming the metal below its recrystallization temperature multiplies dislocation density dramatically. Tangled dislocations cannot move. The metal becomes stronger. Steel grades. Steel is iron with carbon, but there are thousands of different grades. Mild steel has a very low carbon content. It is cheap, weldable, and ductile. Used in structural beams, ship hulls, and pipelines, wherever cost matters most. High-strength, low-alloy steel adds tiny amounts of niobium, vanadium, or titanium. These microalloying elements refine grain size, making the steel much stronger while keeping the same weldability. Used in car body panels, pipelines, and offshore platforms. Tool and die steels contain high carbon plus chromium, molybdenum, and tungsten. After heat treatment, they become extremely hard and retain that hardness even at elevated temperatures, essential for cutting tools and press dies. And stainless steel, add more than 10.5% chromium. An invisible chromium oxide layer forms and self-repairs if scratched. This passive film gives corrosion resistance. Type 304 is the most common, used in cutlery, medical equipment, and kitchens. Non-ferrous alloys. Beyond steel, 4 families of non-ferrous alloys are essential to modern engineering. Aluminium alloys are much lighter than steel. The 2000 series are precipitation hardenable and used in aircraft structures. The 6000 series are weldable and used in bicycle frames and architectural sections. The 7000 series gives the highest strength of all aluminium alloys and is used in aircraft wing spars. Titanium alloys combine low density with high strength and exceptional corrosion resistance. Titanium is also biocompatible. Bone grows directly onto its surface, making it the material of choice for implants. Nickel superalloys retain their strength at temperatures that would destroy ordinary steel. They are used in jet engine turbine blades, often manufactured as single crystals with no grain boundaries at all. And copper alloys, the original engineering material. Brass for valves and fittings, bronze for bearings. Watch the 3 stages. Stage 1. Solution treatment. All solute atoms dissolve into the host matrix. Stage 2. Rapid quench. Solute atoms are trapped. Alloy is now supersaturated. Stage 3. Aging. Tiny precipitate particles form inside the matrix. These particles block dislocation movement far more effectively than individual solute atoms. Result? Much stronger metal from the same base material. Every component requires a specific alloy chosen because its properties match the requirements. An aircraft wing spar must be as strong as possible while being as light as possible. Every gram saved reduces fuel consumption over the entire service life. Aluminium 7000 series is chosen, highest strength aluminium alloy with the best strength to weight ratio. A jet engine turbine blade must maintain its strength at temperatures above 1000 degrees Celsius while spinning under enormous centrifugal stress. Nickel superalloys, often as single crystals, are the only materials capable of this. A hip replacement implant must survive inside the human body for 20 years or more. Titanium is chosen because bone bonds directly to its surface, a property no other structural metal offers. And a gearbox gear requires a hard surface to resist wear, combined with a tough core to absorb impact. Case-hardening steel achieves both, a hard martensitic surface over a tough tempered core, two different microstructures in one component. Let us bring everything together. 4 mechanisms strengthen alloys: solid solution, precipitation hardening, grain boundaries, and work hardening. Steel exists in thousands of grades, each chosen for specific properties. Aluminium alloys are much lighter than steel. The 7000 series gives the highest strength for aerospace. Titanium is biocompatible. Bone bonds to it directly.
Nickel superalloys operate where steel cannot survive.
Every alloy is chosen for a specific reason. In the next episode, Metals Part 4, we look at how and why components actually fail in service. If this video helped you, please like and subscribe. Drop a comment. Which alloy surprised you the most?